Okay, so in this torque review question, it's quite a challenging one. We have this exercise equipment where a person's pulling up an elastic cord, looks like doing some sort of bicep curl, and we have a whole bunch of information here and a couple of questions. So we're considering the arm having a mass of 1.5 kgs. I guess that should say, technically, I want to assume the lower arm has a mass of 1.5 kgs and a center of mass that acts 1/3 of the length of the arm from the elbow. So somewhere around here is the center of mass, so more of the mass would be in the forearm than probably in the hand. So it acts closer to the elbow than to the hand. Tension in the core we're given, this force is 205 newtons. The bicep tendon is acting here on the lower arm 4 centimeters from the elbow. I think that's 4 centimeters along the length of the arm. If the bicep tendon exerts a vertical force on the forearm, what's the magnitude of the bicep force if the arm is at rest? So just holding this in a stationary position, or if the arm has an angular acceleration of 10 rads per second squared, and assume the I arm is a 1/3 ml squared. So there's quite a bit going on in the question, and I will just work on a separate diagram on a full clean page and refer back to this when needed. So the first thing I'm going to do is draw a picture of the arm and then draw in the forces that are on the arm. So I'll try to do this as accurately as possible, and so we can get an idea of the angles that are sort of required. So the arm is at an angle of 39 degrees. So I'll draw this in first. So the lower arm is the object of interest. Going to be the lower arm, and so we know this first angle here is, which will be important, is 39 degrees. Okay, and I haven't drawn this entirely to scale, but I'll draw in a couple of the forces. So we know that the bicep force is acting 4 centimeters from the elbow joint, and it's so this is the bicep tendon, and so I'll call this FB. And then 1/3 of the way from, I'm sure this is exactly, it's almost 9 or 8. So I'll put the weight force here, but 1/3 of the way from the elbow joint, and I'm not drawing these to scale, just drawing them on the diagram, and just for clarity. So this is the weight force on the arm. And then we have a tension force up here that's exerted by the cord on the arm, but we got to think here. We know that from this picture that it's acting at 61 degrees from the positive x-axis, but we're going to figure out what angle this is drawn up here, and that'll be a bit of work. So if I get my protractor and think about where I want to draw here to here, 61 degrees. So it doesn't have to be exact on the diagram, but just for clarity. And I'll draw this force in here, this tension force. Okay, so there are the 3 forces that are on the arm itself. We know that this is 61 degrees. and we want to know that what is the size of the bicep force when the arm is initially at rest, and this is going to be our axis or pivot or axis of rotation. Okay, so you've got three forces, and you've got these are all going to lead to torques. There's also a large force here at the pivot, but it's not been asked for in the question. So any torque exerted by a force at the pivot doesn't exert any torque on the arm, because the R value for that particular force is 0. So about this point, hopefully what you can see here is that the bicep, this will lead to a counterclockwise torque, so that will be positive, but both the weight and the tension lead to clockwise torques, or negative torques. So what we want to have here is a situation where the torque due to the bicep force is equal to the sum of the two torques by the weight and the tension, so that for the arm to have no net torque, the counterclockwise torques must equal to the sum of the clockwise torques. So for the, I'll write this up here, for tau net equal 0, we need the torque F B to be equal to the torque, the weight plus the torque of the tension. Okay, so we can figure out, I'll figure out the torque of the weight first, and then torque tension, then eventually figure out this torque FB. So again, going to this diagram, I'll draw a separate diagram for the weight force. So for the weight force, I'm going to down here so you can see. So I'm going to draw an R vector for the weight force. This would be RW, and we know that's equal to 1/3 of the length of the arm, as given in the question. So back here, the center of mass of the arm acts 1/3 of the length of the arm from the elbow. And then we have the weight force straight down. So in this particular problem, we know this angle in here is 39 degrees. So if you're trying to figure out the torque due to the weight force, I would recommend finding all perpendicular here. So this would be R weight perpendicular. So if you're trying to figure out the torque due to the weight force, I would recommend, zoom in here, just to show you this for a second, a little bit small. You got R weight 39 degrees, and the weight force is straight down, so I'd recommend finding R weight perp times this weight force. Okay, let's go back out. Okay, so for this piece here, so if I just do this separately, the torque due to the weight force is going to be R weight perpendicular times the weight force. The R weight itself, this is going to be RW times the cosine of 39 degrees times the weight, and RW is 1/3 the length of the arm, so I've got 1/3 the length of the arm is 0.3, so it's a 38 centimeter arm, so it's a 0.38 meter length arm. So 0.8 times 0.3, sorry, 1/3 of 0.38 meters times the cosine of 39 degrees. The weight of the arm is going to be 1.5 kgs times 9.8 meters per second squared. I should add in a small negative number, a negative sign here, sorry, because this torque is negative, because it's a clockwise torque. So if you work out those calculations, you should end up at negative 1.45 Newton meters. Alright, so that's the torque due to the weight force. That's negative here. At least that's what its sign is. and I want to figure out the torque due to the tension, because I have the size of the tension force, I have the length, so we can also figure out the torque tension. And that's going to take a little bit of work, a little more geometry than the previous one. So here I'll zoom in on this diagram. I'll use this diagram to help us figure this piece out. So this is a little more challenging. The or vector for the tension will be drawn all the way from the pivot out to where the tension force is applied. But decomposing the or vector is a little bit challenging. See which part of it is perpendicular to the t. I would prefer to decompose the tension force vector into a vector that's perpendicular and parallel to the arm itself. So hopefully you can see this comes from, if I were to decompose it like this, so a vector that runs along the arm and then a vector that is perpendicular, so you're just sort of slightly off. But this piece here is t-perp. So this is where the 90-degree angle is in here, and I really want to do is either figure out what this angle is in here, or figure out what this angle is up here. So you have some choices to make in terms of figuring out what t-perp is, but we don't have enough information at the moment to figure this out, but we can quite quickly. So what you need to notice here is that here's some geometry. You should get a pencil so we don't muddle up everything here. So this angle in here is also 39 degrees. And then I can think, if I think about this large triangle, you could think of this as, in a sense, this is 90 in there. And then you can think about what this angle is. So if you do 180 minus 90 minus 39, this should leave you with 51. And then if you can then think about that the 51 plus this angle in here plus this angle is 180. So this angle in here is going to be 68 degrees. And then you can sort of figure out all your geometry to figure out what this one is 22. So 22 plus 68 is 90 plus 19 there. So you can just sort of work on kind of similar triangles in this diagram to figure out all of the sort of missing angles, to figure out how big is t-perp. I've drawn that, yeah, sort of drawn, it's not really, could have drawn it slightly more accurately. Seems a little bit off, but more like this. Okay, and that's what I'm going to use to solve for the torque tension. So I'll just zoom out here. Okay, so I'll do some proper pen here. So the torque tension in this case, I'm going to use RT times T perp. And the length of R tension is the length of the whole arm. This is 0.38 meters. Again, this is also a negative torque. And then the tension, I can use either tension times the sine of 22 or the tension times the cos of 68, so I'll just use that sine 22. And then we know that this is 205 newtons from the problem here, and times the sine of 22. And I believe that gives you negative 29.2 Newton meters. So, okay, so we've done a lot of the hard work to figure out the two clockwise torques. So, and then just to sort of be clear up here, the these are sort of absolute values. So same as the absolute value of the torque FB, because it's counterclockwise, has to be equal to the sum of the absolute values of these two, because these are clockwise. But if you want to do it technically, you'd have the sum of these three would be equal to 0, but you've got to take into account the sign. So here I've sort of made a small step, thinking that I've just set the clockwise torques, counterclockwise torques equal to the clockwise torques. So here I sort of, in a sense, I'm going to sum these two numbers and then make that equal to the torque FB. So let's switch the color here. So I know that the torque due to the bicep force has to be equal to the sum of those two numbers and have a positive value. So this is 30.6. Hopefully that makes sense why it's positive here. So I can, so if the weight force and the tension force lead to a net torque from those two of negative 30.6. So if I want and they are negative torque, so if I want the net torque to be 0, the torque to the bicep force, which is a positive torque because it tends to rotate the arm counterclockwise, would have to be the positive 30.6, such that the net torque will be 0. So to find the torque FB, so I'll just keep this, I'll do a similar diagram to what I've done over here for the weight force. Again, not drawing this to scale. Now I draw an OR for the OR FB. We know that that's 4 centimeters. In this case, the tension or the bicep force acts straight upward. This is FB. Again, for this example, I would still recommend decomposing the OR vector, but this time, and this is straight up. I can see that this horizontal component here of ORB is perpendicular to FB, so this will be OR FB perp. And I want to set then the torque FB, which would be OR FB perp times FB equals to 30.6 Newton meters. Eventually solve for the bicep force itself. So the torque FB would be OR FB perpendicular times FB, and I'm going to set that equal to 30.6 Newton meters. So FB would be equal to 30.6 Newton meters divided by OR FB perp, which is 30.6 Newton meters divided by, so the length of this is 4 centimeters, so 0.04 meters. And to find the perpendicular component, I would be using the cosine of 39. This is also 39 degrees. And if you work that out in your calculator, you should get this to be 985 newtons. Quite a few steps in this problem to solve for the size of the tension force for when the arm is at rest. And then part B is not too much more difficult because we've done all the sort of hard work here, and we're assuming if the tension force is still 205, the weight force hasn't changed, the torques due to the tension and weight will be the same in part B. We just need to figure out what the new FB is. So again, I've run a lot of room on this page. Left. Again, just looking at this diagram, I just want to again highlight which of these angles. So I'll just write them in here in pen. This is 22. This was sort of 68. This was the 51. This was the 39. So that's how I got all those angles. Okay. So for the next part B of the problem, you were asked to solve for what's the size of the bicep force if the arm has an angular acceleration of 10 radians per second squared. So for this problem, we need to figure out what the net torque is no longer 0. So the tau net is going to be I alpha, which in this case is going to be 1/3 ml squared. That's a rotor, so a rod rotating about one of its ends is 1/3 ml squared. That's what we're going to treat the arm as, and then times alpha. So the torque net will be 1/3 the mass of the arm, 1.5 kgs. It's got a length of 0.38 meters. That has to be squared, and then times 10 radians per second squared. And that works out to be 0.72 newtons. So small net torque. And so we know that the torque net, it's going to be positive because it's a positive angular acceleration, is the torque of Fb plus the torque of the weight plus the torque of the tension. So these have not changed since the previous problem. So the torque Fb in this example, here I'll sort of think about the signs. So torque weight minus torque tension. So I've got 0.72 newtons minus the minus 1.45 newton meters minus the minus 29.2. So in this example, the net torque needs to be a little bit larger than what it was, or the torque Fb needs to be a little bit larger, 31.3 newton meters. So in the previous example, the torque due to the weight, torque due to the bicep force had to be 30.6 to balance out the weight torque and the tension torque, but now we need a little bit of a net torque, so it has to be slightly larger. And again, I would use the same math here. This torque Fb is still going to be equal to RFB perp times Fb. This times is equal to 31.3 newton meters. So again, Fb would be the 31.3 newton meters divided by the 0.04 meters times the cosine of 39 degrees, and this gives you 1008 newtons. So it should make sense that the bicep force has to be slightly larger in case B in order to get the arm to have an angular acceleration rather than to be at rest. Okay, so that should cover both parts A and B.